Today we're taking a look at section 8.7 on systems of equations. And in particular, we're focusing on linear systems in two variables. The section does go on to linear systems in three variables, but we are only doing the ones with two variables. Okay, so linear systems in two variables can be solved by one of three methods. We can use the graphing method, where we graph the two lines and see where they intersect. We can do the elimination method, where we multiply possibly one or both equations numbers and then add them so as to eliminate either x or y. Or we can do substitution method, which is where we solve one equation for one of the variables and then substitute that expression in place of the variable in the second equation. So we're going to take a look at all three methods, and we're going to start with the graphing method. And when we go about solving a system of linear equations in two unknowns or two variables, there are three possible outcomes, and I'm going to kind of divide this here into three sections so we can see three possibilities. The first possibility is that here we have our axes. Here's x and y, and we have one line coming through, and then we have a second line coming through, and the point where the two intersect is the solution to the system. That's basically what's going on when we solve a system. We're trying to find out where the two lines intersect, where to graph them. Second case, and you'll need to add these to your nodes, is where we have two lines that are parallel. And when they're parallel, that means they don't intersect. So notice in case 1 that we call this system consistent, and the lines are independent, and they intersect in a single point. Okay, so that's our solution. In the second case, the lines are parallel. We say the system is inconsistent, but the equations are independent, and our solution set is the empty set because the lines do not intersect. Okay, our third possibility is that when we graph our lines, let me get a different color, that the two equations yield the exact same line. And what we say in that case, that the system is consistent and the equations are dependent, and the solution set is the entire line. So we have an infinite number of solutions in that case. So those are the three possibilities. Alright, so we have a system here we're going to solve by graphing. We have x plus y equals 4. And I'm going to use different colors. Let's use red for that one. And we have 2x minus y equals 2. I'm going to get these in slope-intercept form. So y equals minus 1x plus 4. And let's see, I'll add the y and subtract the 2. 2x minus 2 equals y. Alright, well, I've got more than I need. So just a pivot over on the side. X and y. Okay, so 2, 4, 6, negative 2, negative 4, negative 6, 2, negative 4, 2, 4, 6. Okay, so let's do the one in red. The y-intercept is 4, and the slope is 1, so we can down 1 and to the right 1. I'm going to do down 1 and to the right 1. You can see a good picture, because we need to be very precise on these to get the correct solution. Okay, the second line I'm going to do in blue, and our y-intercept is negative 2. Our slope is 2, so that's 2 over 1. I'll put this one in blue so we know. Okay, so we're going to go up 2 and over 1, up 2 and over 1. That's our point of intersection. So the solution to this system will be the point 2, 2. And we want to check that in both equations. 2 plus, I'm going back to the original. So 2 plus 2 equals 4, that checks. 2 times 2 minus 2 equals 2. 4 minus 2 equals 2. So that one checks. So checked it in both. So here's your solution set right there. Okay, our next method is the elimination method, and this is where we want to somehow change the two equations or change one of the two equations so that we eliminate x or y when we add two equations. So as I look at these, right now they're not set up for either one to be eliminated. Let's choose to eliminate the y. You could also choose to eliminate the x, so that it would not be incorrect to do that. So I'm going to multiply the top equation by 2. Multiply by 2. So I'll get 8x plus 6y equals 2. Notice we multiply everything on both sides. Now, I decided to eliminate the y, so I need to multiply the bottom one by -3. So that we have a positive 6y and then a negative 6y. And so that's what we mean, that we want them to be opposite. So -3 times -9x minus 6y equals -6. So -x equals -4. Multiplying or dividing by -1, we get x is 4. Now we choose one of the equations, and it really doesn't matter which one. So I'll just take the first one, 4 times 4 plus 3y equals 1. 12 plus 3y equals 1. If we subtract 12, we get 3y equals -11. And divide by 3, we get y is 11/3. -11/3. And I want to check something. That doesn't sound right. Alright, let me double check my numbers, make sure. Okay. So I multiplied by 2 and got 8x plus 6y equals 2. Multiply the bottom one by -3. I get -9x, -6y, and -6. When I add, I get -4 and -x. So x is 4, which is correct. 4 times 4 is not 12. Let's see what I did wrong. It should be 16. I bet you were sitting there saying, "Can't you see it? I see what's wrong." Okay. Alright, so now we subtract 16. You get 3y equals -15 and divide by 3. And so y is -5. So we get the ordered pair 4, -5. Now, sometimes when you do the elimination method, you'll get a true statement. You won't have any variables left. You'll get 0 equals 0 or -10 equals -10. If you get a true statement, then what that means is that the two equations are the same line. So the answer would be set of all x, y such that, and you want to put the equation. If in the case we got it with this, we could put such that 4x plus 3y equals 1. Okay, so if that happens. Sometimes you will get a false statement. You'll get something like 0 equals -10. In that case, the lines are parallel. Which means the solution set is the empty set. Okay, so those are two things that may crop up as you're working on these problems. Alright, substitution method is our last method, so let's take a look at that. To solve a system by substitution, we want to solve one equation for one variable in terms of the other. So as I look at these, I see an x is isolated there. So that's going to be the easiest one to isolate. We're going to subtract 2y. So I now know x is equal to -2y. So if I take -3x, and in place of x, I'm going to put negative 2y. I now have the equation in one variable. So this is equation 2, that's equation 1. So I'm working on equation 2, put in equation 1. Okay, so now I have 6y minus 5y equals negative 17. And negative times the negative would be a positive. Okay, and we're still subtracting, so y equals negative 17. Okay, it looks like I copied two different problems, so that should be interesting. Okay, so let's go back to the equation number 2. X is what I don't know, plus 2 times negative 17 equals 0. X minus 34 equals 0. That means x is 34. So we're getting, whoops, not negative, positive. Positive 34, negative 17. And again, you may want to go back and check those in both equations to make sure they work out. And again, you may get the same sort of situation you did with the elimination method. If you get a true statement, again, it'll be the same line. It'll be the entire line as your solution. And so you'll need the to put the whole line as your solution, the set of all x such that set of all xy such that y equals 3 plus x, or whatever the equation is. So set builder notation. Or if you get a false statement, the lines are parallel and there is no solution.